physicists see surprisingly strong light, high heat from nanogaps between plasmonic electrodes. Seeing light emerge from a nanoscale experiment didn't come as a big surprise to Rice University physicists, but it got their attention when that light was 10,000 times brighter than they expected. Researchers from the Rice University and the University of Colorado Boulder discovered this massive emission from a nanoscale gap between two electrodes made of plasmonic materials, particularly gold. The lab had found a few years ago that excited electrons leaping the gap, a phenomenon known as tunneling, created a larger voltage than if there were no gap in the metallic platforms. In the new study in the American Chemical Society journal Nanoletters, when these hot electrons were created by electrons driven to tunnel between gold electrodes, their recombination with holes emitted bright light, and the greater the input voltage, the brighter the light. The effect depends upon the metal's plasmons, ripples of energy that flow across its surface. The researchers formed several metals into microscopic bow-tie shaped electrodes with nano gaps, a test bed developed by the lab that lets them perform simultaneous electron transport and optical spectroscopy. Gold was the best performer among electrodes they tried, including compounds with plasmon damping chromium and palladium chosen to help define the plasmon's part in the phenomenon. If the plasmon's only role is to help couple the light out, then the difference between working with gold and something like palladium might be a factor of 20 or 50. The fact that it is a factor of 10,000 tells that something different is going on. The reason appears to be that plasmons decay almost immediately into hot electrons and holes. Through the spectrum of emitted light, the researchers' measurements reveal those hot carriers are really hot, reaching temperatures above 3000 degrees Fahrenheit, while the electrodes stay relatively cool even with a modest input of about 1 volt. That continuous churning using current to kick the material into generating more electrons and holes gives this steady state hot distribution of carrier. The discovery could be useful in the advance of optoelectronics and quantum optics, the study of light-matter interactions at vanishingly small scales.